Hi, my name is Kevin Binns, and today I'm going to be discussing semirings as generative theoretical devices. To get a handle on group theory, what you need to do is you need to go back to what you learned about addition and multiplication back in elementary school. So as you remember, addition supports the associativity, which is defined here, and also commutativity, a plus b is b plus a. What's more, addition supports an identity element, a plus 0 equals a, and an inverse element, negative a plus a is 0. And lastly, addition is grounded in the axiom of closure, which is defined as if I add any two integers, the result must also be an integer. And these five axioms together uniquely characterize addition. You need nothing else. Now, it turns out that if you turn your gaze next to multiplication, you require a very similar set of five axioms. You also require closure, associativity, identity, inverse, and commutativity. The only difference, marked in color here, is the name of the identity element and the name of the inverse element. And the core insight of group theory is you can leverage these similarities. You can say these two operations over a set are two different types of the same thing. And we'll define this thing as having an interface that accepts a set, an operator, and an identity element. And we'll call this combination of five axioms an abelian group. So in this picture, we can say if I give it the set of all integers C, and the operator plus, and the identity element 0, we can reconstruct what we know and love as addition. And we can do the same with multiplication, and we can do the same with much more arcane algebraic structures. And that's what a group is. Now, what's so special about these five axioms? Can we have a group that has instead four axioms? And it turns out that the answer is yes. So let's define each axiom as a bit to simplify our taxonomy somewhat. And an abelian group then is a 5-bit string 11111, and we can define 32 different combinations of axioms, 2 to the 5th, right? And I've reproduced 6 of the more common group categories here, with their bit strings and their common names. Now, moving on to ring theory, the core insight of ring theory is, what if I want to reason about a set with more than one operator? So the insight in ring theory is you can glue two different operators together, and you can do this by using distributivity to define how the second operator interoperates with the first. So at the end, if you glue two abelian groups together, say addition and multiplication over addition, and you glue them with distributivity, you get a field. And you can also play this axiom shaving game and define a whole host of different ring categories. And I've reproduced 6 here. And you can see that there are a whole host of different types of rings, and semirings is only just one element in this family. So what's so special about semirings? Why do we discuss them more than any other thing? And it turns out that Chomsky discovered a connection between semirings and context-free grammars back in the 1960s. So if you have a toy grammar, say you have a grammar with this set of rules, you can generate sentences. And it turns out that for many grammars, you can generate an infinite recursive set of sentences. And in this toy grammar, I've reproduced 2. And it turns out that if you take the set of output sentences and you want to associate a probabilistic weight to each of them, that turns out to be a useful thing to do often. You can represent that set of weights as a formal powered series, or a set of coefficients A1, A2, etc. And the family of this formal power series is itself a semiring. That's something called the Chomsky-Schutzenberger theorem. Alright, so now that we understand why semirings are useful, let's see them in practice. So let's zoom into natural language processing, the dynamic programming algorithm called the CKY parser. And it turns out that there's a recognition algorithm and the insight algorithm. And the key insight in dynamic programming in general is dynamic programming is isomorphic to logic programming, and you can boil down dynamic programs into something called item descriptions. And as you can see in the, this is exactly what we do in this image below. We take, say, these two phrases, and you'll notice that they're very similar, and we can boil them into the very same item. And the same goes for the rest of the items in this list. And here's where semirings fit into the picture. If we take a recognition semiring and we plug it into this generic item description, out pops our original algorithm. And the same goes for an inside semiring, out pops the original inside algorithm. So we can see that semirings at their core are kind of Swiss Army knife plugins that plug into an algorithmic structure and out pops something new. Alright, now I'd like to spend a few minutes, I should say, discussing different algebraic properties. So it turns out that if you're designing a semiring-based algorithm that requires an explicit ordering, you have to be willing to give up the commutativity axiom. If you're wanting to reason about an inference problem across an infinite loop, for example, loopy belief propagation, you need to beef up your rings with the continuity axiom, which basically requires a supremum be defined across an infinite set. And finally, if you are willing to break ties arbitrarily, the cost of that is you lose the associativity axioms. Alright, now moving on to a new space. So these semirings are useful in describing other algorithms, but what about new semirings? Is it possible to design entirely new semirings that answer novel questions not before considered? So some people have done some work in collecting various sets of semirings and how they relate to various inference frameworks. Here's one such table here. And the question is this table complete? Is there something in these combination operators? Can we add more operators to them and derive more useful semirings? And what I'd like to do is discuss a tool that we can use to facilitate this semiring design called the lifting trick. And what you do in the lifting trick is you take a semiring that is known to be useful. For example, here we have an expectation semiring that computes first-order statistics in a training machine learning context. So you take this useful semiring, and what you do is you apply the lifting trick and something useful comes out. So what you do specifically is you copy the semiring and you duplicate it, and then you nest the two together. You concatenate them into this one more complex unit, which is shown down here. And what you do now is you apply the original logic, these two original rules, to this semiring, and you derive something new. So let's step through the algebra step by step so you understand what's going on. So what we're going to do first is we can think of these aggregation rules as kind of a color remapping, as this particular color remapping. And applied to a more complex structure, it looks like this. So you go red, green, blue, yellow, becomes this color shape here. Alright, and next what we do is we take the result and we kind of plug it back into a semiring. We take the original multiplication and we plug it into semiring multiplication here, and we take the original addition and we plug it back into semiring addition here. And then we can remap the colors, so now we're ready to play the same aggregation rule again. In this case 3 times. One here, and one here. And next we play the coloring game, and now we're ready to apply the combination rule here. And lastly, all we do is we take this final result and we flatten it. So it stops being a jagged array and becomes just a one-dimensional array. And that's our result. And it turns out that that result is something called a variance semiring, which is useful in its own right. You can use it to derive, for example, gradients of the derivatives of the statistics generated by this algorithm. And it's used in practice in a software program by software engineers across the world. Alright, so in conclusion, abstract algebra generally sheds light on inference concerns and serves as an organizational tool for typical algorithm design. And we've explored Semiring design, which complements algorithm design.